Okay, everybody, in this video it's gonna be a very brief video, but what we're going to do is play around with the idea of amplitude and how we can change the amplitude of a graph by adjusting the function or the trig function that we're graphing. Okay, so I think the best thing to do is just kind of start with this. Start with some graphs that we know the shape of. Didn't want to do that, sorry about that. Let's move. Let's undo that, hopefully. Escape. There, that works better. Get our pen tool out here. Well, we got this to work. Okay, so anyways, essentially, let's start with the graph maybe of y equals sine of x. What do we know about y equals sine of x? Well, it has a period of 2 pi. That is, it takes it 2 pi's worth of input before it starts repeating its y values again. So if I had to sketch this, we basically, starting at 0, so at 0, we'd go out 2 pi units past this. Okay, we take that 2 pi, we'll cut it in half, pi. Cut those halves in half, and we know the basic shape of sine of x is just goes one above, one below. So we say it starts on the ground, a fourth of the way through its period, it's up in the air. Half the way through its period, it's back on the ground. 3/4 of the way through its period, it's back down to -1, and then back up to the ground. We say this is a graph of y equals sine of x. Okay. My question is this: what if we start playing around with like y equals 2 times sine of x? What might one basically suspect would happen to the original graph of sine? And so I think maybe if we switched over, I'd like blue on this example. What would happen here? Essentially what's going to happen is it's going to double all of our y values. So what you'll see is it actually takes us up to a height of 2 and a height of -2. So it still started at a height of 0. A fourth of the way through its period, it's going to go up to its high point. Halfway through its period, it's going to go down to its ground level again. 3/4 of the way through its period, it's going to go down to its minimum and then back up to its ground level. So what you see is something that has the same period, a period of 2 pi, to do its thing, but basically the amplitude, which was, by the way, a measure of how far north and south it deviates from this center line. It went 2 above, 2 below. And quite technically, the definition of amplitude, let's recall this, the amplitude, we say A is equal to 1/2 the absolute value of the maximum value minus the minimum value, where in this case, the maximum value was a height of 2, and the minimum value was a height of -2. We're saying that's a total span, really, of 4 units. So half of 4 is 2. So we say, okay, so 1/2 absolute value of 2 was our maximum minus our minimum of -2. So we say 1/2 absolute value of 2 plus 2, really. And so 1/2 absolute value of 4 is 2. Amplitude is 2. But the easy way to do this is just to say, well, this number out front here, the absolute value of it, is going to give us the amplitude. It's going to go 2 above, 2 below. I think the best thing to do is just kind of come over here into our graphing utility, and we'll get some of this garbage or this mess out of the way. It's definitely not garbage. And just start playing around with things. So like, for example, this effect of the number we're multiplying by our trig function here. If we say y equals sine x, we'll get this graph we're very familiar with. Starts at ground level, goes up to its maximum, then back to ground level, minimum, then ground level, up, down, down, up. We said, okay, so if we start calling it y equals 2 sine x, you notice that it's a graph that has just twice the original amplitude. What if we were to say, now y equals 3 sine x? It is not a shocker, but you'll see something that is now, goes 3 above and 3 below its center line that it's deviating from. It deviates 3 above and 3 below, but it still has the same period. Okay. Hey, same thing's going to happen with cosine. If we were to play around with cosine and say y equals 1 cosine of x, it has an amplitude of 1 because it deviates 1 above and 1 below its center line. Okay. But the same period, to start up at 1, it takes it 2 pi's worth of x values to get back to a height of 1 again. So we say, what if we say y equals 2 cosine of x? You'll notice that it doubles its amplitude. It still starts up in the air. A fourth of the way through its 2 pi period, it's down at the ground level still. And then a half the way through its period at pi, we're down at its minimum at a -2 now height. We say 3/4 of the way through its period, it's back up to ground level, and then all the way through its period at 2 pi, now it's up at a height of 2 again, but it still has a period of 2 pi because it started at a height of 2, went through 2 pi's worth of x values to get back to a height of 2. Again, what if we said y equals 3 cosine x? Okay, oops, we want cosine of x, not cos x. And we say it just adjusts its amplitude. I need people to know also that this pattern exists for graphs other than sine or cosine. So like for example, y equals, let's put cosine of x in here. What if we were to graph y equals secant of x? We know that secant is the reciprocal of this, and so wherever our cosine graph is at a height of 0, our secant graph is undefined, okay? Wherever our cosine graph is either at a height of +1 or -1, our secant graph, its reciprocal, is also at those heights. And then we have our basic secant graph. So what if we wanted to graph, say, y equals 2 secant x? Well, we get a secant graph that is essentially a little bit higher up in the air, up at a height of 2 and down at a height of -2. But that's because that would be the reciprocal of y equals 2 cosine x, which would also, getting these original ones out of the way there, since y equals 2 cosine of x would have an amplitude of 2, then the secant graph would be up a little bit higher. What if we were y equals 1/4 the secant of x? So 1/4, get that parenthesis out of the way, secant of x. It's now got the same period. Okay, same period as the original cosine graph, which is 2 pi. It's just that instead of being up at a height of 1 and -1, it'd be at a height of about 1/4, and we can just show this. This would be the reciprocal of y equals 1/4 cosine of x, right there. Okay, so it would abut that graph. Okay, but still be undefined, where cosine would be at a height of 0. And then last but not least, what about tangent? What if we played around with, say, tangent? Okay, well, we know tangent has a period of just pi. And it looks like this, and it's undefined at pi halves, and then every pi units past pi halves, because of course it repeats every pi units, and so if it's undefined at pi halves, every pi units we go past that, it'll also be undefined, okay, and repeats itself. So what if we did y equals, say, 3 tangent x, okay? Where before at, say here, if you can see this, at pi/4, our original tangent graph was at a height of 1. Now our new tangent graph is up at a height of 3. Oops, let me adjust this point a little bit here. Is at a height of 3. There, that's close enough. And where before our original tangent graph was at a height of -1, okay, roughly speaking, down here, our new tangent graph would be at a height of -3. Okay, so -3, 0, and then 3 instead of -1, 0, and 1. So essentially, that number that we're sticking out in front of our trig function, like this number here, okay, has a direct impact upon the amplitude of our graph. We say the absolute value of that number is the amplitude of our sine and cosine graphs, and that definitely affects, therefore, secant and cosecant graphs, because those would be the reciprocals of the original sine and cosine graphs. So yes, that is a discussion of how this coefficient of our trig function there, when we graph them, affects the amplitude of our graphs.